Hello, everyone. Welcome to the September session of Dr. Spotfire. My name is Neil Canungo, your host, and we're going to go ahead and get started today. Today, we are talking about time series anomaly detection with TensorFlow deep learning. I'm joined today by two other data scientists, David Katz and Sweta Kotha, and the three of us will be showing you this great new dashboard in DXP that we have going on for deep learning anomaly detection. Now, a big kind of announcement, we are going to change our delivery format starting in October. We are no longer going to use the registration in Zoom. We're going to switch to live streaming. What this means is you'll no longer have to fill out the registration form. We will continue doing our sessions on the first Tuesday of every month at 9 a.m. Pacific, but we'll be live streaming to these four platforms. You can watch on any one of these platforms, and you can ask your question directly in the chat from these platforms. It's also a great time to join our user group so you can make sure and you catch these live streams. I'm going to put the user group links in the chat for you today. Just put those in there for you if you want to join our Facebook group, YouTube channel, our Twitter account, follow us on Twitter, or follow on LinkedIn, follow me on LinkedIn, and join our LinkedIn group. So this will start on October 5th, our next session, and I'll send some more details via email on this change. Kind of a big operational change in how we're doing things, but hopefully makes it easier for people to attend sessions. All right, so next up, I wanted to say that we have TIPCO Now coming up at the end of the month. There is a free track that you can register to and catch the keynotes. There's also a paid track where you can get certified with Spotfire and you can get training as well as see additional sessions. You can see more of the breakouts, participate in the collaboration and discussion. I'll be there collaborating, having open conversations with people. So consider the free track or even the paid track if you want some a bigger experience. And with the session we're doing today, this is actually going to be expanded on during TIPCO Now with our Chief Analytics Officer, Michael O'Connell, and data scientist, Adam Faskowitz. They'll be talking about practical AI in action, anomaly detection, and pattern classification, going over a variety of solutions using Spotfire, Team Studio, TIPCO products to identify anomalies and do anomaly detection. Okay, so to get started with today's session, I have a few slides just to set the context of what we're talking about today. And first, what is an anomaly? An anomaly is going to be data that is outside of the bounds of typical range where you have a variable operating or a variable measuring. So here you see these different black points, and this could be this is actually sales over time. There's normal sales, and you can see it kind of following this pattern. What could be considered normal is anything within this green range. And then there's these anomalies. There's some very low sales during this period and very high sales during this period. Those anomalies are in red. Now that green band can be defined by various ways. There are control limits. There's a lot of science behind control limits. It could be something just as simple as a standard deviation. They could be different measures of variance that you might look at. But that's outside the bounds of what we're discussing today. Just wanted to talk about anomaly as something outside of your expected values. So today's DXP is going to take some input data and it's going to use deep learning to learn the time series. It's then going to reconstruct the signals and detect anomalies among that time series and then certain cluster signatures. And the autoencoder is this kind of center part that's going to be doing the deep learning that's going to take that input data, it's going to compress it down, it's going to then reconstruct those signals and be used to detect the anomalies. So the data that you're kind of feeding in, so a normal time series you might feed in might look, something like this, but something that it's going to do is start to fit a reconstructed curve. It's going to look at or reconstructed function. So it's going to look at the data coming in, reconstruct what it thinks it should look like, and using a neural network, it's going to do this and after that, what's outside of that are going to be our anomalies. So more specifically, what is an autoencoder? I thought this was a really good description from a Medium author. Autoencoder is a unsupervised artificial neural network that learns how to efficiently compress and encode data, then learns how to reconstruct the data back from the reduced encoded representation to a representation that is as close to the original input as possible. Autoencoder by design reduces the data dimensions by learning how to ignore the noise in the data. And when we're looking at anomalies, we want to be able to determine, are certain data points noise or are they actually anomalies? And there's various sophisticated ways to do that. Today, we're going to use the autoencoder to do that. And so autoencoders can be used in different ways. This is a denoising, image denoising autoencoder example where there's a lot of noise in this image and these pixels, and that's fed into this neural network. It's compressed and then it's reconstructed, and the noise is actually removed from the data. And this can be used not just with images. This type of stuff can be used with audio signals, sensors on equipment, credit card transactions, things like that. How do we remove the noise from what's actually an anomaly we want to measure? Now we're going to be doing multivariate anomaly detection. Now, why are we doing multivariate anomaly detection? Multivariate is going to allow us to see more complex interactions between the variables and these components and how they contribute to a true anomaly. So on the left here, you can see there's one dimension where there's this point and it doesn't look like an anomaly. It's between the upper control limit and the lower control limit. It's totally within the bounds. And then on this variable, on this dimension, this point is also within the upper and lower control limit, and it looks totally fine. However, when you look at them both together, you'll see that this typically operates in this band, and these two orange points contribute to an anomaly here that you wouldn't have seen if you were looking at this in a univariate fashion. So this would show, there's a bad tester right here. This is looking at different test stations, and there's a whole bunch of points right here that indicates there could be a bad tester over there that you can see when you look at this in a multivariate fashion. Now, this is looking at two dimensions. We're going to actually go ahead and cluster these. And why should we cluster our signatures? Well, what we're looking at is if let's say we have a lot of different anomalies, a lot of different variables that are interacting, and let's say you said I want three well, the clusters allow us, let me say it this way, the clusters allow us to look at multiple dimensions easier. We're limited in what we can see on a two-dimensional screen. You can maybe visualize let me stop doing this. You can maybe visualize three dimensions. You can see three-dimensional clusters, but once you start getting into higher order dimensions, you can't quite visualize all these interactions and what are potential anomalies. So by clustering them, we can see which variables contribute to, which are the components that contribute to certain anomalies, and we'll choose the anomalies, or we'll choose the clusters, excuse me, by looking at an elbow plot, which we'll show later. And what we're trying to do is look at the Euclidean distance between points. And this has a cluster here. This has a cluster here. This is minimizing the total sum of squares of the Euclidean distance between these points. And what that's doing is creating very tight clusters without too much variance. Now, if we get the wrong number of clusters here, let's say, or we don't do it granular enough, let's say I said three clusters, it might try to do something like this, right? And if it does something like this, then, well, these points are pretty far from those points. And so you're getting a really large distance there, and that's not a really good cluster. So instead of doing three clusters, by doing six clusters or five clusters that are shown here, you're getting better. Now, if we do too many clusters, then you're just going to have a hard time observing what is actually what's a true signature that you're trying to measure. So this could create it more difficult to interpret. So there's an optimization there on how do we get the right number of clusters that we can interpret unique signatures, but we don't have too few clusters that there's a lot of noise in our clusters and a lot of variance in our clusters. All right, so let me take off my pen and so this is going to be the clustering analysis will be the last thing we do. I'm going to jump into the DXP, but just to mention the types of anomaly detection, I mentioned credit card fraud. There's also intrusion detection, fault detection, networking, manufacturing, system health monitoring, ecosystem disturbances, anomaly detection for product quality. So anomaly detection can be used in a variety of industries. This example we're going to show is going to involve a power plant data. So with that, let me go ahead and open up our DXP. And this DXP is built as a template. And we are going to try and put this on our community. So keep an eye out for that. I'll put that link on the video description of this on YouTube whenever it's ready. But the first page of this is to take your data from your local drive, and you can hit replace data, and they'll bring your own data into this template. And then you can start to explore the data by looking at different variables. You want to look at x-axis, we want to look at time. Maybe I want to look at pressure, or I want to look at this waste gas. These are different variables I can look here. If I want to see how if I want to see the modality of the data, if I want to see the distribution of the data, I can also change the histogram here and look at that data. And this is very simply showing the average and plus and minus one standard deviation. So there's a lot of data points outside these standard deviations, and that's fine. This is just to give you a sense of where the center of the data is. But this is, as you can see, not normally distributed data. So of course, we're going to have data that's outside of the standard deviations. So whenever you figure out which data you want to work with, maybe you want to work with a subset of data, or you want to work with a a subset of data that's within a certain range and try to find anomalies within there. I'm going to select all the data, and I'm going to actually hit create summaries, and that's going to create these summaries for analysis. And then I can go into model, and here I can split this into a training, validation, and test set. So this is all the data that was brought in and these different rows of data. I'm going to select here, I'm going to select some data for training. I'll select that. I'll mark that as training data. And this is actually using Spotfire as an application to then set my training data, my validation data, and my testing data. And we're going to, after I show how this all works, or actually after I show what this does, we're going to show how this all works. So I'm now going to set my testing data, and we have a training, validation, and test. I'm going to make this validation a little bit larger here. Okay. Now below here, we want the variables, we want the predictors we want to use for classification. So I want to use actually my numeric variables with exception of this real date. And I'm going to actually classify this as a predictor. So this is using blobs, and this is using data functions in Spotfire to actually classify that data. This ID, I want to make this into an ID type, and I'm going to update that, and you can see that it made it a key. And then below here is our data function that is reaching into TensorFlow and running a neural network with Google TensorFlow to build a model. So I can hit create model, and you'll see this running. This does take about 30 seconds to a minute to run. But what it's doing is it's using a Python data function to go into Google TensorFlow based off of these parameters. It's storing the model on my local drive. And it's using these input parameters that you see here: a learning rate, dropout ratio, the number of hidden layers, activation functions. And Sweta is going to talk about this in just a moment. Give this a second to finish computing. And I'll go ahead and move forward while this is. Oh, it won't let me. Let's see. This is still going to be running in the background, but I'll just use the cache results while this runs, and you might see this change after it's done. So when it's done, it's going to create this type of reconstruction over time. And we can move this outlier cutoff, and you'll see that it'll change this number here. So after you run the model, it's going to create this reconstruction over time, and it's going to give you these results. So I can move the outlier cutoff. If I move it pretty high here, it'll say how many incidents are above this train sample. Now, an incident is an event where you might have multiple anomalies in a sequence or in consecutive anomalies. Like let's say you have 10 anomalies consecutively, that might be a failure incident. And so we have an automated way to count the incidents. Now, if I make this outlier cutoff too high, it's not detecting any real incidents up there. I can make it lower. It's saying there's 31 incidents. And it's looking at just the training data, by the way. So it's looking at the training data. And let's say I want to look at this incident. I'm seeing a spike here. I can select this and let's see here. I can select this and I'm seeing the average component contribution that's contributing to this anomaly. Now, if I select the contribution, so there's these variables here, right? So this potential incident and this DP2 differential pressure 2 is contributing the most to it. So the raw data is down here. This chart is the same as this. And then this one over here is the raw data signal. And then what you're seeing in the middle here is a reconstruction error of just this component. So what this means is that it tried to reconstruct this signal, but there was a certain errors. It found the actual data points were far off from what the neural net believes that the signal should be. And from there, it's telling you, okay, well, these might be real anomalies because the neural net doesn't believe that there should be data points over here. And so since we're looking at this in a multivariate fashion, different variables are contributing to this anomaly. And these are how much the different variables are contributing to the anomaly. So when you get below that, so now we're going to look at how do we cluster this. There's a lot of data to look at. There's a lot of different incidents we could look at. There's a lot of different variables to look at. And so we're in a very high dimensional space. So we want to cluster this. This elbow plot is looking at the sum of squares, and where it starts to get to 4 or 5, really when you're at like 6 clusters or you're at 15 clusters, you're not really going to have a big change in the reduction of variance or the reduction of the sum of squares that you're looking at your clusters. So here, let's say we'll do 5 clusters. I'll make this 5 clusters, and I'll hit build those clusters. And what it's doing is it just built 5 clusters down here. Now this is showing us the variables that are contributing to the the different anomalies, but it's looking at the number of incidents. So cluster 2 has a lot of incidents in it, but cluster 2 also has it's also pretty flat here, and it's looking at so it could be a lot of noise here, whereas cluster 1 and cluster 3 have a lot of information coming from differential pressure 6 as well as differential pressure 1 here in cluster 2. So they're a little bit more interesting. If I'm looking at this power plant and I want to make an adjustment, I don't want to make an adjustment to all of my variables. I want to look at making an adjustment to certain variables here. So since this has all of the data in it, you're seeing cluster 1, cluster 4, you're seeing these clusters in here and the variables connected to it. The thickness of the line is a measure of that error, the average component error. So it's a representation of what you were seeing, essentially what you were seeing right here. This is that average component error. So that's what you're seeing again here. Now, if I want to filter this down a little bit or filter this up, I want to remove some of the noise in this. So that's why you're seeing this change, because I'm taking out some of the lower error reconstructions. And that is saying, okay, those might be noise, and I can focus more on the variables that are contributing each cluster. So cluster 4 has the product per minute, differential pressure 4, and differential pressure 2, all contributing to incidents then in that cluster. Cluster 3 has just differential pressure 1 contributing to the anomaly in that cluster. And we can scroll down and see, okay, that cluster 3, that yellow one, that's when it occurred. This is over time. These are when these different anomalies occurred. So it's pretty complex, a little, it's a very sophisticated application, I would say. There's a lot going on here. And now I want to take some time to bring in David and Sweta to talk about how this all works and how we built this. And David, I thought I would start actually right on this page with the incidents. And can you tell the audience a little bit about David designed a lot of the math and the operations and the data science behind this. So David, can you tell us how you came up with your methodology for determining incidents?
Sure. Thank you, Neil. The the idea here is to build on some very established methods where people are generally looking at things from a univariate point of view. And years ago, there was a method developed at Western Electric that became very popular. It's called the Western Electric rules. And the idea it was that you have some anomalies that are very severe, just but they might just be one point in time, and other anomalies might be more moderate, but they persist over time. So Western Electric came up with some rules where you would recognize these two types of anomalies. And I took the second method and said, if an anomaly persists for at least 5 timestamps, then I would focus in on that and call that an incident. It's more than just something that happened one moment in time. A lot of times in a manufacturing context, you'd be looking at things that affected yield. So if it's rare enough so that it happens just as a blip, you might not be as interested in something that persists over time. So what happens in this DXP is, the severity, which was the first part of the Western Electric rules, is controlled by this cutoff. So the slider on the left there lets the user decide, where to make that cutoff to say what an outlier is. And each time you do that, that triggers a data function in the background to count the number of separate incidents. So in this case, the cutoff is so high that the resulting incidence above cutoff value is 0. There are no cases where it stays above our cutoff 5 times in a row. But if you adjust that, you get a new value. Now there's just 1. Okay, so what you might want to do is just play with your domain expertise and what you're looking for and so on, and decide where to put the cutoff so you find an interesting number of these incidents. And that begins the next step in this process. If you have a fairly large number of incidents, then you can begin to cluster them. With a very small number, they're just kind of individual events. But if you have a number of them, then they begin to be something that repeats over time. Each time, of course, it has some duration, but over time you can start to recognize these. It's not like each one of them is unique. Over time, you begin to recognize that some of them recur over time, and that can be very useful.
Thanks, David. Yeah, I think that the way that you can drill down on each of these components really helps too, because there's a lot going on with all of these variables. So we have this RLE fast, and that runs to just calculate the number of cutoffs. It's just a very quick script to calculate the number of cutoffs, and um, it's looking at the RMSE here, and once it has a cutoff, it then runs the RLE2, right, David? And that,
Yeah, basically, when I originally did it, it seemed logical to do both functions at once, not only to count the number of incidents, but to record them in a table for further analysis. But that turned out to be awkward in terms of the speed of response within the template. So RLE fast just does a count and does not try to build a table in addition, so that you get the nice, you can show that again. Once you show the slider again, Neil, so they can see what I'm talking about. Yeah, so when you have this outlier cutoff, it automatically triggers RLE fast to get you this number, in this case, 32 incidents, and that happens very fast. Once you've done that, you've chosen it, and you want to go ahead with your clustering to use those 32, you actually do some of that work over again, which ordinarily you wouldn't want to do, but here it has a specific reason. You wanted to get that fast response for the user, and then when you want to delve into the table, the resulting table, you rebuild that in the next step, when you start to do the elbow plot.
and going down to this elbow plot, can you tell us a little bit about the rationale on the elbow plot?
Yeah, the elbow plot is not really specific to anomaly detection. It really is a tool that's often used with k-means or other clustering methods. In a lot of applications, as Neil was alluding to, it's often the case that you don't have, there's not an absolute right answer. You want to find something that's useful for conceptualizing and following up going forward. So there's actually a number of different methods. This is probably the oldest and most popular method, which is often called an elbow plot, which just refers to the shape of the curve, where as you add more clusters, you're able to explain more and more of the variance by which cluster you place objects in. And at a certain point, it flattens out. And somebody thought that reminded them of an elbow, but the name stuck. But basically, there's no point. In this case, after you have about 4 or 5 clusters in your analysis, there's not a lot of point in adding additional ones. You can run the algorithm. You can end up with more cluster definitions, but you're not really explaining very much more. So although the definition of where you put that vertical line is, it's basically a visual kind of rule of thumb. It's people have not gone to the extent of making that just a calculation. But depending on what you're trying to do, Spotfire makes it easy to play around with where that cutoff is of how many clusters that you find useful, and the elbow plot is basically a guide to what you might find.
Yeah, and just for example, I put in 10 clusters here, and you can see there's now 10 different colors, and a lot of these are pretty similar to each other. Cluster 9, cluster 5, they seem to be pretty similar to me. There's a lot of noise in cluster 1 there, I think, or, it's pretty flat, not a lot of error being measured. As you start to add more clusters, I think it just gets harder to interpret. So you want to find kind of the minimum number of clusters that will, as you said, David, explain the most amount of variance, right? That's kind of your balance.
Yeah, so I see another question in the Q&A box.
Mhm.
And if I understand correctly, you're asking about implementing alternative methods, and that's where the flexibility of data functions come in a Spotfire environment. So that if you decided you wanted to use, for example, density-based clustering, you'd go into the code and make a change or build a new data function that would then fit into this structure, which makes it easy for less technical users to make use of these functions and do their work. A lot of times we conceptualize the use of Spotfire into authors and consumers, right? So the author might go in and use their knowledge of Python or R to enhance or construct something like this. One way to look at this is an example or a starting point for an expert to customize it for a particular use case.
Right, and we have a combination of R and Python, the same application here. The RLE functions were done in R, and Sweta built the autoencoder with TensorFlow and Python. Sweta, do you want to tell us a little bit about how you built that, how the neural network works, how how people can build data functions themselves? And I'll let you
Yeah,
go ahead and
sure.
share your screen here.
Yeah, sure. I'll bring it up. Okay. So a lot of the time when we develop these data functions, it might help us to work in a separate IDE outside of Spotfire. So for example, here, if I'm working on a TensorFlow autoencoder, I started off by working in Jupyter Notebook, and it also helps us see how this code is being used. So I'll actually walk through this exact code that's being used in a template here in Jupyter Notebook. So what we're doing, or I should start at the beginning and say that Neil mentioned that TensorFlow is a common Python library used for neural networks, but it has both low-level and high-level APIs for, in general, for machine learning algorithms and artificial intelligence. And what we're using here is TensorFlow with the Keras API. So Keras is a high-level API that has an integration with TensorFlow versions 2.0 and greater. And it's specifically designed for working with neural networks. So in the code itself, what we do is we, of course, want to define our input parameters. So you'll notice that a lot of data functions take in standard inputs, whether it's data tables, columns, or other types of values. So the model data that we're actually reading in is the same user table that we saw in the template. And I've split up the other input parameters into two separate ones. We have inputs that are just needed for the function in order to run. And we also have inputs that are specific to the actual neural network itself. And you'll see some of these include the activation, learning rate, types of optimizers, etc. So I want to mention that at first, this is a lot to look at. There's a lot of inputs here. But one thing we'll actually notice is that the only required input parameters we have to specify to the data function is the model data. And that's pretty crucial because that means that someone without that much expertise in deep learning can come in and still be able to run these data functions and then later maybe tweak some of the parameters if they wish. So I actually want to dive in or spend most of the time looking at the actual TensorFlow code and see how this is going to be used within our data functions. So I'm kind of skimming past this area that does a lot of the data preparation. As you can imagine, we have to modify our input data before it's actually fed to the neural networks. And I'll go to the section over here that's on training the model itself. So one thing that we want to do is be able to save our any of the models that we've created. So in TensorFlow plus Keras, we can save models as a lightweight option using H5 files. So any of the models that we construct, you can save locally to your own directories. And the actual model that we're creating is in a fully connected autoencoder. So this is almost your typical or regular autoencoder, where when you define sequential layers, they're going to feed forward to each other. So the type of cells we're using are just a typical neural network cell. And some of the, and using Keras, actually, we can use some pretty interesting tricks in order to help us with neural network training. So what I've done here is actually define some model callbacks. And you can see me calling tf.keras. So this is calling the Keras integration from TensorFlow. And I'm defining callbacks for early stopping of training and model checkpoint. So early stopping essentially means we're tracking our loss function. So whatever loss the neural network is trying to optimize, and we're trying to see when it reaches some sort of minimum. When we reach some sort of minimum over a long span of time, then we know that training's about done. So that's what we're doing in this callback. And I've also added in a callback in order to save the best model. We don't want multiple models being saved after each iteration or after each epoch. We just want the best one saved. And the last callback that's optionally defined is this one called reduce learning rate on plateau. So in neural network training, we often want to manipulate the learning rate that's used in order to gradually decrease it. I think it's most common to see the learning rate being gradually decreased so that you can try to have your try to have your function converge, or you can try to reach a minimum point. So that's what we're doing when we call this callback here. And these are just some of the things that are checked after each epoch or after each iteration during training. And the next thing that we want to look at is the actual architecture itself. So here we're defining a sequential architecture. And like I said before, this just means that any layers we define are going to be run sequentially. And you can see the previous parameters that I mentioned being called here. So for example, model activation, model optimizer, learning rate. And you'll notice the way that these parameters are being defined is in the standard check, like it's an if statement check, and then you can see something being defined for model activation. So what's actually going on here is that I previously mentioned that a lot of these neural network specific input parameters are optional. So in order to check for this within a data function, we want to see if model activation is being specified by a user. And if it is specified, then we take whatever activation they provide us. But if it's not specified, then we need to provide a default. So here I'm setting all the defaults for these neural network related parameters. So the default model activation is ReLU, or rectified linear unit. The default model optimizer is Atom. And we also set default learning rates within the optimizers. And you can also see that we have default number of epochs, and also the loss function too. So the default loss function we use is Hubert loss, as opposed to a mean squared error. So Hubert loss is used in robust regression, and it's also something you can try to experiment with. So in addition to the neural network related parameters, we have to define the actual architecture. So a user can actually go ahead and define their own autoencoder architecture, but if they don't give us one, we'll just provide a standard one. And the standard architecture is going to be 250 by 200. So this means that the first hidden layer has 200 neurons, the second hidden layer, or the reduced dimension of this overall autoencoder, has 50 neurons, and the last layer has 200 neurons before we output whatever number of features we have in our data set. And in order to actually create the architecture, we need to add it into our sequential model. So you can see here, I'm doing model.add dense. And dense is basically a declaration that we're using regular neural networks. In other words, fully connected layers. And optionally, we can also add dropout. So dropout is just the act of randomly removing certain neurons during training. And this helps prevent overfitting during training. So if you have a dropout ratio of like 0.5, that means during training, we're actually removing 50% of our neurons, while during evaluation, we use our complete neural network. And again, since we're in Python, since we're in Jupyter Notebook, we can actually print out our model summary just to see how it looks. And we call standard functions to compile and train our model. And here we can print out the training per each epoch or per each iteration of model learning. And lastly, what we do is we actually format this model learning into some sort of table. And this is actually one of the outputs of the data functions, because we want to be able to see how our model is learning over time. So for example, you can plot the loss, the training loss versus the validation loss in Spotfire. And that's one of the visuals that we previously saw. And there's a ton of other things that we can actually do with TensorFlow. I just thought I'd mention a quick couple. We can get different metrics per each split. So for example, if we're working with test, train, and validation splits, we want to know what our overall metrics of interest are per each split. So maybe we're concerned with the mean squared error after creating some type of model. And in Spotfire, you might want to create KPIs for these using this data function or using this data table, or you might want to like plot them on a scatter plot. And another capability is that we can also get the intermediates from the autoencoder itself. And what I mean by this is that Neil previously mentioned that the autoencoder is also a technique for dimension reduction. So that middle layer of an autoencoder, we can actually extract it. And in Spotfire, it'd be very interesting to either write it to a table or maybe save it as a binary document property. So that's something you can feed to other algorithms or visualize itself. And so this is the exact script that was slightly modified in this autoencoder template. And you'll notice that, again, there's only 4 required parameters here in this autoencoder data function. So this is the input data that we previously saw. And I slightly modified that generic TensorFlow autoencoder code so that we're also taking account a few other things like time interval, a splits data frame, variable info. These are all things that come from free from previous steps in this template. So we're essentially just making sure we have some of these pre-existing data tables as well as our input data. And then that's all you need to actually run this TensorFlow data function. And if a user wishes, they can always modify the rest of these neural network related parameters.
Sorry, I was on mute. Thanks for showing that. Can you show in the scripts tab of this data function? So you just brought in, so you developed in Jupyter Notebook, your Python IDE of choice, and then you just brought your script in here, and you created those input parameters that you had on the next tab, and the input parameters and the output parameters. So this just wires up for you the data that's in the Spotfire dashboard, and then using this, you're able to now have Spotfire be this kind of nice interface that uses your algorithm, and you don't have to necessarily go through and have you don't have to have a business user going through your code. They can just interact very intuitively with the dashboard with the DXP.
Right, exactly. So from my end, it was very easy to actually tweak that Python code to work within the script. I think this is the only additional code that was added in, and this is just working with some of the existing data tables that we had previously in this template. And if anyone wants to be able to run this data function, they don't need any knowledge of what these parameters truly are. They can be able to run it as it's already configured, or if they wish, they can go ahead and modify some of these parameters that we've just set up using document properties.
Yeah, and we also have some questions, and someone's asking if we could provide that notebook online. What we're going to do is we're going to put that in the community as a template for this Autoencoder DXP, and you can find the script there. So we'll just be submitting that for legal approvals. It might take a couple weeks, and again, keep a lookout for the video description on the YouTube recording of this video, and you'll be able to find that template. We have another question that was on what basis was the number of neurons decided?
Yeah, so it's it really depends on the actual data set that you're working with, and it's deciding on the number of neurons is a matter of hyperparameter tuning. So for default, I set 250, 200 because I think that's a small enough autoencoder structure, and it takes any input data, and if our input data has only 10 columns and it's expanding it to a greater number of neurons within the first layer itself. So that's pretty different from actually condensing the number of neurons like we're doing here if we take something that's 64, 32, 10. So it's truly actually just a matter of playing around with these hyperparameters and seeing how the loss changes. Sometimes you can get drastically different results depending on your data, or sometimes it doesn't change too much at all.
Have you ever considered any automated approaches to your hyperparameter tuning for something like this? Such as, automatically trying different permutations of hidden layers, and I know we reduced the number of epochs and compared our results that way.
Yeah, so that's not implemented in the current data function, but it would be a great way to actually to perform hyperparameter tuning, or even like cross-validation. So you can imagine that maybe we want to specify a list of epochs or a list of hidden layers so that we can try all those different types of combinations and output the model with maybe, I don't know, the best metric, whether that's like mean squared error or we're aiming to minimize the loss. So that's a thought for future consideration, and perhaps with iterations of the TensorFlow autoencoder data function that we release, we can include that.
Right. We have a lot of questions popping up. I'm going to take a break from the questions just to show a few tips on the styling here. So just to give folks a little bit of insight onto how we made this look this way. Now, one is a trick that I use pretty often, which is to make a scrolling page. You go to page layout. Where is it? Page layout. So you got to be on the page. You go to page layout, and then just make that page really tall. So height, when the height is less than 2500, it will use a fixed page size. But since I made this so tall, it's going to make a scrolling page for me there. And this initial analysis was split across, I don't know, maybe like 8 or 10 different pages. And so I reconsolidated these into single scrolling pages so that the markings and everything could all be on the same page and people weren't having to jump between different pages. So that's definitely been something we've had positive feedback on for usability. You might notice these fonts here. Now, I took a page out of John Henderson's book. If you all have seen the Dr. Spotfire session from a few months ago on creating electrifying dashboards with ERCOT data, John Henderson of Enertel showed us some tricks on how to use different fonts. And what you can do is you can go to Google Fonts and you can actually filter down if you want serif, sans serif. A sans serif is a font that doesn't have anything kind of on the end here, whereas a serif font is kind of like Times New Roman. Well, we could just show you right here. A sans serif font is like this, and a serif font is like that. And I kind of just found something, I wanted something monospace, which means that every character takes the same number of spaces. Maybe we'll do a whole session on just using typography and fonts, but you can go and you can select it. You can choose whichever style that you want. It'll put it to the side here for you. You select at import. So this is the CSS style tag that I want to use. I went ahead and I developed this inside VS Code. So let me bring that over from my other screen. Jump to the top here. And so I copied and pasted that import URL. So I just took that, I took multiple fonts that I wanted and I put that at the top of my code. And where were we here? And then when I want the font family, you can use this. You can copy that. Let's say I wanted a different font here. You can add new fonts into this. But I took that font family and I put that whenever I would have a different header. Here's my H1, H2, H3, different header. I put that in. Now to override a lot of the Spotfire stuff, before your semicolon, you want to put this exclamation mark and important, and that'll tell it to use your CSS styling. So I built this whole style sheet for this, how list items should look, how calculate values should work. And what I'd recommend is, taking some of this code, this will again be in the DXP, but taking this code and looking at, okay, I have a button group and how buttons look like in Spotfire. Text box, I have how text box is hovered and focused, right? So this is all in the button group, right? So what I would do is make sure that you have something for each of these elements by copying and pasting this, and then just adjusting some of the different parameters here, the different I would say not parameters, but values here for those styles. So once you have your style sheet, you can just go into your text area and you can create. I created this as you could put this at the top and inside style divs, inside style tags. But I created this as an embedded JavaScript so I could have it across each page easier. And I just copy and pasted all of my style in here. So this took me a little while. It took me, like an evening to do all of this, but whenever I had it done, I think it was really worth the time to put that style in here. And you'll notice that instead of having traditional default styling of text areas, I actually used my div class h1 for model results. That's my header one. I use body paragraph for this text. I used HR for a horizontal line there. I used a subtitle a header for what this reconstruction is. So that allowed me to standardize how the fonts and everything looked across each page. Um, on this page, I added some. I also had some gradients behind. On each page, I had gradients behind the text box, and just to make it look more consistent, I've just put this horizontal line across this for each of this sections. So I had part one, part two, part three here. And you can get the gradients from, let's see, what did I use for the gradients? Uh, the gradients here, I use the CSS gradient.io, and you can design your own gradients here. This page, let me have this page load all the way. Yeah, you can design different gradients here. Looks like their page isn't loading completely right now, but there should be some options here for you. Okay, I'm going to take a look at some of the questions, and then we'll wrap up the session. So we had a question from Peter Shaw around wondering, since we are analyzing the time series, let me pull this up on the second page here. Since we're analyzing the time series, do you perform any kind of autocorrelation analysis to see whether a time series is long enough to split up into training and testing? And does that time series need to be detrended or difference before sending into this DXP? David, do you want to answer that question?
Sure. Detrending could certainly be a good idea if the data exhibits a strong trend. It's a little tricky because now you're looking at many variables and trying to detrend them all, but it's definitely a good approach. Another approach is something I call striping, is like in the data rows panel, where you have the time series of all the observations, and you can divide them into training, validation, test. I've had some success in using not continuous time periods, but several time periods spread across the whole time interval. In other words, you would create a set of stripes representing the training and validation sets that are interleaved with each other. And that gives you kind of the best of both worlds, because the model can then look at data from different time periods, but you still have a lot of points that are contiguous to one another.
Thanks, David. There's a question on the hyperparameter tuning on whether or not you could use grid search. You absolutely could use grid search. We didn't put it in here, but you could put that in as a data function and use grid search as well there. There was also a question on how do we retrain models. Well, you would just simply create another model here. So the model path is actually saved to my desktop right now. So these are H5 files, and you can create new models. Last question I'll take, and then we'll wrap up. Someone was asking, how do you reach out for help if you need help and you get stuck doing this? Again, at the beginning of the session, I put some user groups. That would be my recommendation. If you have something that's very sensitive, business sensitive, you can email us at drspotfire@tipco.com. But the fastest way to get an answer when you get stuck is to actually ask questions in their Reddit. Our subreddit's very active. Our Facebook group's really active. A lot of people helping each other there, and we like to answer questions there too for the benefit of the whole community. I'll put those links in the video description of this recording as well. So I think that wraps it up for today's session. Thank you so much for joining. Thank you, Sweta and David, for joining as well. This was a great session, hard work, I think, from the data scientists here, and I think it paid off. I think we had a lot of good questions and a lot of people interested in in this project. So thank you again, David and Sweda, and thank you all for joining. We'll see you in October.